Although the tools like Routh and RootLocus provide us very good information about stability, they do require us to understand and actually have a model or a transfer function of our system. One of the really compelling reasons to use frequency domain methods is because it's often possible to essentially drive your system with different sinusoids and observe the magnitude and phase changes in the output. And so that's essentially empirically forming a model of the system using frequency response. And so Nyquist stability is the heart of understanding stability from a frequency domain perspective. Before we can formally state the Nyquist stability theorem, it's useful to kind of build up our intuition and some of our tools. And so this is going to be built on what's called Cauchy's argument principle. And this is the idea that if we do have a transfer function, again, we're motivating this based on the fact that we don't have the transfer function, but in order to prove these ideas, we can use the transfer function. So our transfer function is going to be this h of s, and it's going to be composed of essentially all the zeros multiplied together, all the poles multiplied together. And we're going to create a contour C, this contour right here, that is simple and closed. And so simple just means that it doesn't intersect itself. And we're going to place this contour in the right half plane. And if all of our poles and zeros are in the left half plane, then what we're going to do is we're going to observe the angles of the resulting motion as a test point S0 tracks along this contour C. So another way of expressing this is to write the transfer function evaluated at S0. We're going to write that transfer function in terms of its magnitudes and phases. And so, for example, this distance between the first zero and the test point S0, the magnitude is given by the length of that line, and the angle is given by psi 1, and so that means that the overall transfer function includes that magnitude and that angle. And so just like we showed in RootLocus, that these magnitudes can multiply, all the zeros multiply in the numerator, all the pole magnitudes multiply in the denominator, and that produces the overall magnitude of the transfer function evaluated at this S0. And then the phase of the result, the phase of the complex number that's represented by h of s of 0, the phase is represented by the sum of all the zeros and then subtracting away the sum of all of the pole angles. And again, these angles are always measured from the horizontal, from these poles to the line that extends to that test point. And so something to observe is that these angles, they start at some value, and then because this is a closed loop, you're going to return back along this contour back to that same point. And so all of these angles, phi 1, psi 1, phi 2, these will all return back to the values that they started from. In addition, notice that if all of these poles and zeros are located in the left half plane, that the biggest value you could possibly have is 90, and the smallest possible value you could have is minus 90. And that would be if this contour C was very close to this imaginary axis, and you had a pole or a zero directly on this imaginary axis, then you could imagine that you'd have an angle that would be very close to 90, or if it extended below, an angle very close to minus 90. And so the Nyquist stability criterion is going to essentially draw out the magnitude and phase of this transfer function evaluated along a contour. And so we're going to pick a very special contour in a couple slides. But for now, let's just think about this generic circular contour, and that would produce a plot of essentially h evaluated on that contour. So each point, so this is the value, s hat is in fact h evaluated at S0. And so this has a magnitude and a phase. And the magnitude is, again, this distance from the origin. And the phase alpha that's going to be changing as S0 moves around this contour, alpha is just given by the sum of these zero angles, and then the difference, they're subtracting off then the sum of the pole angles. And again, these are going to be changing as S0 changes. And so what ends up happening is the most that's going to happen is that this is going to wind around, but it's going to eventually return back to where it started, because that's what all of these angles do. If we place a pole or zero inside this contour, then something different happens. So what happens to this phi 3 in this case is that it may start at some angle, say for example 120, but then as this test point moves around the contour, it doesn't return back to 120, it moves back to 120 plus 360. And so what we observe that this angle phi 3 actually experiences a 360 degree rotation, which is different than the angles phi 1, psi 1, and phi 2, which are not contained inside the contour. And what this means is that then the angle alpha, which is being traced in this plane, the imaginary value of h and the real value of h, that this experiences a 360 degree rotation. So previously, when there was no pole or zero inside the contour, then alpha didn't circle around the origin because it didn't make a 360 degree rotation. And so what we're observing here is that if we place a pole or zero inside this contour, then alpha sees the impact of this 360 degree rotation, because that's one of these angles is actually experiencing that same 360 degree rotation. And so what happens is that if a pole is inside the contour, that one of our angles phi undergo a 360 degree net change. If a zero is inside the contour, then one of our psi variables undergo a 360 net change. And so because of the sign orientation on which this happens, then the psi's correspond to a positive or a clockwise rotation, and because of the negative sign in front of the pole angles, the pole being inside the contour corresponds to a counterclockwise rotation of alpha. And so this leads us to a theorem that lets us get closer to stating the Nyquist stability criterion. And that says that if we have some sort of this complex function, which is our transfer function, and the contour map of all those points, so that's the points in the right-hand side of all the plots I just showed, so that will encircle the origin z minus p times in the clockwise direction, where z is the number of zeros and p is the number of poles inside that contour. All right, and so you can imagine we're talking about stability, and so the poles that we care about are the poles that are in the right half plane of the closed loop transfer function. And so that's what we're going to get to next. We're going to exploit this concept in order to study essentially the role of the zeros and poles of a transfer function and whether they sit inside the contour. And so we're going to pick a contour that helps us identify things in the right half plane. And so throughout this discussion and through all discussions, note that that you can count a counterclockwise rotation as a negative clockwise rotation. So the negative of a clockwise rotation is a counterclockwise, and the negative of a counterclockwise is a clockwise rotation. All right, so now moving towards the actual statement of the Nyquist stability theorem, we're going to introduce two main ideas. And so number one is that the poles of the closed loop transfer function are equal to the roots or the zeros of 1 plus k times g. And that's simply because this is the denominator of the closed loop transfer function. So 1 plus k times g is the denominator of the closed loop transfer function, and so whenever it's 0, that means that s is a pole of the original closed loop transfer function. So it's actually the roots or the zeros of 1 plus kg that gives us information about the poles of the closed loop transfer function. And so for stability, we're really interested in right-hand poles, right half plane poles, because those are the ones that are going to create an unstable system. And so the contour that we're going to pick, it's a relatively tricky contour, is this very large contour that essentially spans all the way along the imaginary axis out to positive infinity, and then wraps around at the magnitude of s at infinity, and then comes back to negative infinity at the imaginary axis, and then comes back along that way. And so that's the contour that we're going to use the Cauchy argument theorem on. And so again, we're going to map using a transfer function, and the transfer function we're going to pick is that one that corresponds to the denominator of the closed loop transfer function. And so we're going to be interested in counting the number of encirclements of the origin when we use this curve, which is gotten by h of s, which is the denominator of our closed loop transfer function. We can make our lives just a little bit easier by changing the transfer function that we analyze, and just by analyzing k times g and moving over the point that's being encircled. So instead of encircling the origin, now we shift everything over, and we're now encircling the point -1. And so we're just getting rid of, the previous definition was h of s was 1 plus k times g of s, and we were looking at encirclements around 0, and now we're going to essentially subtract 1 off both sides, and that's going to lead us to now looking at encirclements around -1 instead. And so the reason why this particular contour works is the fact that for any physical system, g of s, the transfer function, is going to go to 0 if the magnitude of s goes off to infinity. And so what that means is that as we get out to this magnitude of infinity out here, all of this evaluates to 0. All of these points that I've just squiggled in red all get mapped to this point that is effectively at 0, because all of these evaluate, g of s evaluates at 0. And so what's left is simply just the imaginary axis here. And so that is exactly the information that we have from frequency response and what's on the Bode plot. And that's what we're going to use to compose the Nyquist plots and compose the Nyquist stability theorem. And so essentially what we're doing is we're evaluating, depending on our gain, we're evaluating this g of I omega, which is again the imaginary axis. And something that we can observe is that there's some nice symmetry here, and so what we can really do is just plot for positive omega values, and then we can reflect this across the real axis, and that gives us the symmetry that we would expect based on, for example, just the complex conjugates. The second piece that we're going to use in order to complete this the Nyquist stability theorem is to observe that the poles of the open loop transfer function g are in fact the poles of 1 plus k times g. So we already identified that this is important because it's the denominator of the closed loop transfer function. And so Cauchy's argument principle uses information about the zeros and about the poles of h of s. And so h of s, we said we were going to pick to be, h of s we decided was going to be k times g. And so now it's important to understand the poles and zeros of this. We already know the zeros correspond to the closed loop poles, and now what we're seeing is that the poles of this quantity are essentially the poles of the open loop transfer function. And so we can see that if we write G as essentially this n of s over d of s, numerator and denominator, that 1 plus k times g of s, you notice we could just get common denominators, and now we can rewrite this, and you can see that d of s still gives the denominator of 1 plus k times g. And so the poles of the open loop transfer function G are in fact the poles of 1 plus k times g. And again, we're really going to be interested in the right half plane poles. And so using Cauchy's argument theorem, it says that the number of counterclockwise encirclements of, in this case, -1 and not 0, because we're looking at k times g as our transfer function, that's going to be equal to the number of zeros of 1 plus kg and minus then the number of poles of 1 plus kg. So again, 1 plus kg is the thing that we're going to be evaluating. And so in using Cauchy's argument principle, we're going to stick the number of zeros there and the number of poles there. And in particular, we're going to be looking at the number of poles and zeros that are inside this contour. And so that means that we're looking at, again, here, the right half plane poles, and again, the right half plane zeros of 1 plus kg. All right, and so if the zeros of 1 plus kg, if this quantity of the zeros of this correspond to the poles of the closed loop transfer function, and we're talking about the right half plane ones, then we really want this quantity to be 0 if the closed loop system is going to be stable. So the closed loop transfer function cannot have any poles in the right half plane if we want it to be stable. So we need this quantity z to be equal to 0. And what that implies is that for stability to happen, the number of clockwise encirclements of -1 need to be equal to minus the number of right half plane poles of 1 plus kg. And this, remember, this quantity we just said, number 2, is in fact the number of right half plane poles of g of s. So now we're still using information about our open loop system to understand stability of our closed loop system. And this allows us to finally state the Nyquist stability theorem, which says that the closed loop system is stable, and this is an exact condition, if and only if the number of counterclockwise encirclements of -1 on the Nyquist plot equals the number of unstable open loop poles. So unstable open loop poles, these are the right half plane poles of g of s. And that has to be equal to the number of counterclockwise encirclements of -1. On the previous slide, we had number of clockwise encirclements of -1 has to be equal to minus p, where this was the number of right half plane poles. And so we bring this minus sign over here, and that creates counterclockwise encirclements. And so kind of a corollary to this says that if we already have an open loop system that is stable, then the closed loop system is stable if and only if this Nyquist plot doesn't make any encirclements of -1. So if you have an open loop system that's stable, there can be no encirclements of -1 if you want your closed loop transfer function to be stable.